But for the last talk of the day, we've got Stephen Morris from Toronto, who will tell us about the different sort of melting problem. But one which
freezing.
Well, there's melting too.
Yeah, there's melting.
But it's really quite interesting, and I've known about it for a while now. Just one with that, Stephen.
Thank you. Thank you, Gideon. I promise you that this talk will be different than every other talk you've heard at this meeting so far. I hope in a good way, but maybe not. You can tell me. I'm going to tell you about experiments primarily. My talk is about 95% about curious phenomena which we know experimentally, and about 5% of my talk is about failed or half-baked theories of why these phenomena occur. And I promise you that by the time we get to the end, you'll see why this might be relevant to something that you know something about. But you got to wait to the bitter end before you find that out. It's amusing to be here at Cambridge talking about icicles because I actually started the icicle experiment while I was on sabbatical in 2005 in the cold room over at Pavilion H over there. So I can honestly say that I have been working on the morphology of icicles experimentally for more than 10 years, which when you tell people that, they think you're nuts. But I hope you will see that I haven't wasted my time, but maybe I have, you know. I have been ably helped in this project by PhD student Anthony Chen, who most of the data I will show you was generated by Anthony Chen. And John Layden is a newer PhD student who is working, even as we speak, on the theory, which I will get to at the very end, as well as experiments. And all these other people in between are able, and perhaps some of them undergraduate physics and engineering students who have helped us with the mechanics of the experiment through the years. Yes, I'm going to talk about icicles, and that's a very Canadian topic. Every winter we see icicles pretty routinely, but I remember coming to Cambridge and giving a talk at BP about icicles, and like the next day there were icicles hanging on the shed outside of BP, and that's like never happens in Cambridge. And I think it's just because I was here, is how it went. Okay, well, what is an icicle? An icicle is an ice formation, and you don't make ice without taking water at 0 degrees and removing a certain amount of latent heat from it and forming ice at 0 degrees. So an icicle ice formation is fundamentally a heat transfer kind of problem. And in the case of icicles, you supply some water, ideally very close to 0 degrees, and you let it drip from some overhanging support, like your roof or something. And it starts to form a ice formation. And then subsequently, the water runs over the surface of that ice formation in a thin film flow. And some of it, usually some of it anyway, drips off the end. And some of that water that's running over the surface freezes and grows the icicle, and some of it drips off the end. So it's a kind of funny problem. You control maybe the temperature and the rate at which you put the water in, but you don't control the shape. The shape chooses itself from the process of growth. And it's a fluid mechanics problem and a heat transfer problem. The surface is covered with flowing water, and somehow the heat that's going to produce the ice has to be extracted through that flowing water in order to add to the ice. And there's another phenomenon in nature that we probably recognize that has a similar look to it, fluid mechanically, and that's a stalactite. So while an icicle is determined, its shape is determined by where the heat is removed, a stalactite is determined by where carbon dioxide is removed from a solution of calcium carbonate, and that changes the chemistry of the solution and deposits this solid calcium carbonate onto the evolving shape. So fluid mechanically, there's quite a bit of similarity between the two. There are many subtle differences between the two, and I'll come back to some of these points later. But there actually are theories which look quite similar for the shape, the morphology of stalactites and the morphology of icicles. The key difference, of course, is that icicles grow in a few hours. Stalactites can take 100,000 years to grow. So these are practical things to study in the laboratory, and these things are somewhat impractical to study in the laboratory. But they're both examples of an interesting kind of pattern formation, which, as we always say, is ubiquitous in nature. You start with some kind of shape. You allow fluid to flow over water to flow over it. It could be turbulent. It could be thin film, something like that. And something happens, erosion, transport, deposition, dissolution, or in our case, some kind of growth. And that causes the surface to evolve its shape slowly. And the only scale separation here is between the time it takes the water to run down the hill and the time it takes for the slope to evolve. This evolves slowly compared to the water flow time. And then there's a kind of funny feedback between the shape and the flow, and that determines the emergence pattern of the thing. And this really is a thing that is ubiquitous in nature. You can look at all kinds of natural processes, glaciers, river valleys, mountains that are eroded by the rain and so on. And all these things have this kind of feedback between the flowing fluid and the shape. And it's a kind of a nice naturalistic thing to study. So icicles actually are quite subtle when you start to look at all the different ways that the ice grows. There are at least 3 different ways that an icicle grows. One is the obvious way. The tip gets longer. It turns out that the heat transfer from this exposed tip is fast because part of the heat is carried away by the droplets that fall off the tip. And so what you get there is essentially crystals of ice growing into a bulk fluid, bulk liquid water at the tip. And that water, the drip size is determined by surface tension, so it doesn't get any smaller than a few millimeters in size. And so that's kind of normal ice growth into what turns out to be supercooled water at the tip. And that causes the tip to extend. The second way it can grow is it gets fatter around the circumference because water is wetting the whole surface and running down the outside, and some of that water freezes to make the icicle fatter. Oh, something I forgot to mention about the tip, which is interesting, is quite often there's a large volume of unfrozen water up inside here, and you can even sometimes see bubbles inside of icicles. So icicles are actually little pipes, and you might say, well, why doesn't the water inside the pipe freeze? So the answer is the whole icicle, as long as the water is running over, as long as it's actively growing, is very, very close to the equilibrium freezing temperature, and there's no temperature gradients left in there to carry the latent heat away. So this stuff won't actually freeze. So it actually usually freezes by leaking heat up through the solid and into the roof or whatever is holding it up. So if you ever see an icicle, if you're so fortunate as to see an icicle which is actively growing, you can take a pin or something and stick it up and see how far you can see. You can find this water column up inside. What usually happens, of course, is the thing stops growing because the water supply stops, and then the whole thing freezes solid, and then it's not hollow inside after that. So the third mode of growth is this pipe-filling growth, which is hard to observe, but it happens eventually. There's enough heat transfer through the root or somewhere to freeze the water inside the icicle. So there's 3 different modes of growth. We'll be concerned with mode 2 exclusively, pretty much, for this talk. We've also studied other aspects of the icicle growing, the tip and the shape and so on, but I'm going to focus on one aspect of the whole phenomena in this talk, which is the ripple pattern, which we'll come to in a moment. Because heat and CO2 diffuse differently, there actually are some important differences between stalactites and icicles. So for example, you can get stalactites which are only tip growth, essentially, and not growth on the sides, little pipes. And these are called soda straws, and they're essentially a little pipe that self-organizes, a little drip falls off the end, and just adds to the length of the pipe, and it gets longer and longer. It's very delicate. But you don't see this in ice, and the reason you don't is that the heat would escape from the inside of the pipe, and the pipe would freeze, or it would freeze on the outside. But because heat and CO2 behave differently, you get formations in stalactites that have no analog in ice. And the reverse is also true. There are ice formations which have no analog in stalactites. Another difference is the icicle is made from the water, so the water can be consumed as it runs down the icicle. And it can even all be consumed before it reaches the tip, and I'll show you that later. But that doesn't happen in the calcium carbonate case. All the water that comes onto this thing drips off, and only the tiny little bit of calcium carbonate which is dissolved adds to the shape. That's one reason why they're so slow. Another difference is cave formations, of course, grow much more slowly, but they also involve the escape of carbon dioxide into the air, and that doesn't change the buoyancy or the fluid mechanics of the air around the icicle, around the stalactite.
Just a question. You said that these stalactites form by creation of calcium carbonate?
Correct.
So isn't that an absorption of CO2?
No, it's the CO2 leaves the solution, it changes the pH of the solution, and that causes the calcium carbonate equilibrium to change, and then it precipitates calcium carbonate.
So there's no hope of using this for sequestration?
The carbon dioxide that's doing the job comes from the atmosphere.
Okay.
So one of the main things people do, and I'll show you a picture of this later, is they take stalactites and they saw them in half, and and they date the carbon or the oxygen, I guess, isotopes in them to get, and all that's come from the atmosphere.
But it is a sink for CO2.
Yeah, but there are better ways.
Okay.
Don't buy stock in, stalactite sinks for CO2.
But that's my startup.
Slow start, real slow. Okay, so it turns out the fluid mechanics of icicle growth is much more complicated because the icicle is the warmest thing in the environment. It's at 0 degrees. The surrounding air might be 10 or 20 degrees colder than that, and so there's a lot of fluid mechanics going on around the icicle typically. So the icicles I'm going to show you are ventilated and there's turbulence going on. In the cave, everything is very slow and still and diffusive, and you don't need to worry about that. And so this is a pretty formation called a drapery, where the drip runs down the sort of leading edge of this thing and drips off down here and makes this amazing thing. It looks like curtains, but it's actually solid rock. Okay, now you can study icicles for a few weeks a year in Toronto, and it's a very frustrating business because they're usually way high up and you've got to climb ladders to get them. So we built a machine. So what you do is you just take a box and you refrigerate the box and you arrange for water to be delivered into a support in the box, and you wait maybe 8 hours and an icicle will form on the support. It's a little subtler than that. We actually rotate the point of support. The point of support is a little piece of wood. The water that's pumped in comes in via a peristaltic pump through a nozzle which is slightly off axis, and the point of support rotates once every 5 minutes. So if you watch this experiment in real time, it's very, very boring, okay? The icicle does not look like it's doing anything. You can see the drips falling off, but you can't see the support move because it's going so slow. The nozzle is put slightly off-center in order to get the water to be distributed uniformly around the point of the support. The other reason for rotating it is we actually take the data by taking images of the icicle 8 times per rotation and detecting the edges of the icicle in the images. So this allows you to take a complete 3D scan, if you like, of the icicle every 5 minutes or so. The last reason for rotating it is that we want to encourage it to be axis symmetric, so we rotate it slowly for the same reason as you might rotate your meat in your barbecue slowly in order to get it cooked nicely on all sides. So it looks like the icicle is ripping around really fast, but in fact the experiment is almost, quasi-static. It's almost excruciatingly slow to watch. Every second of this movie is about 10 minutes of real time. Another slight complexity is we need to control the humidity and the air motion inside the box. We actually have fans inside the box. We measure and control the humidity, and we have a warm funnel at the bottom, so when the water drips off, it goes in the funnel, and we can measure the weight of the frozen water. We can measure the flow rate in and the flow rate out, and we can measure the temperature and the humidity and the air motion, and we can control the composition of the water, and we can basically do everything you want to know about the icicle. Okay, so this icicle I'm showing you here is a rather ideal-looking icicle. It's quite transparent, and it has a nice, smooth shape. This, of course, is not the first icicle that you would make. You would naturally start the experiment with tap water, like every normal person would. You're debugging the experiment, you start with tap water. If you grow a tap water icicle, it looks more like this, okay? Now, I'm not showing you the icicle rotating here. What I'm showing you is the same icicle growing 8 times from 8 different rotational positions. So I have 8 pictures per rotation. I animate them in groups of orientation so you can see it over and over again. But it's turning 1/8 of rotation between each one. You will notice immediately that it doesn't look like the previous icicle. You'll notice that it is a little bit foggy, and it has a pronounced undulation or ripple pattern on the outside. This is what a tap water icicle looks like. And it's also what many natural icicles look like. So it turns out, to make a very long story short, the strongest parameter that changes the morphology of the icicles is not the temperature, not the air flow rate, not the water flow rate, but the composition of the water. The one I showed you before was all smooth. That's distilled water. This one has a tiny, tiny level of impurity in it because it's made of tap water, and it has a ripple pattern on it. Okay? So this is one of these funny experiments where we actually set out to study the ripple pattern. We built the experiment. We ran the tap water through it. Everything rippled nicely. We thought, okay, now we're off. Then we did a slightly more controlled experiment. We used distilled water, and the ripples went away. Okay? So there should be a name for this, like a Gedunken experiment, only a Geplunken experiment. It's like You set out to study what seems like an obvious phenomenon, you do a controlled experiment, and the phenomenon disappears. Okay? So it turns out that purity of the water is a crucial, crucial thing. So the whole talk is basically from henceforth about purity of the water. Yeah?
Is the change in optical depth, is that because it's polycrystalline? Or
Yes, they're both polycrystalline. But I pointed that out to this audience because I suspect, without being able to prove it, that the fogginess is caused by liquid water at the grain boundaries or something like that. They're different. They're different in appearance because there's something that isn't just transparent ice in this one. Okay. So what about these ripples? Here are some pictures of natural icicles with ripples. It's quite easy to see these in nature. This one grew on the side of my house. This one grew on my top deck, and this one I have to admit that I pulled it off Flickr. Flickr is a great resource for images. It's got 5 billion images on it. If you need a picture of anything, you just hunt through Flickr and somebody has taken a picture of it, whatever it is. So I got permission from the guy who took this, who's some lawyer in Utah, and I put it in a scientific paper because it's such a beautiful picture of the ripples. So this, you can see the ripples are not particularly regular looking, but they're sort of, sinusoidal things. Here's the best picture I've ever found of natural icicle ripples. Here the light is shining through a bunch of icicles from behind, and the focusing effect allows you to see them quite clearly. And the first thing you'll notice is they're all extremely uniform. They're very typically close to 1 centimeter in wavelength. And that turns out to be one of the strangest features of icicle ripples, is they're very robustly always the same, independent of flow rate or temperature. And I'll show you data about that. Icicle ripples have an amusing history. I first started working on the icicle experiment because I'd seen the ripples in natural icicles, and then I read a paper by Ogawa and Furukawa, who claimed to have a theory for the formation of the ripples. And subsequently, Kazuto Ueno wrote many papers which they basically have different theories, which I won't go into much detail about Ogawa's theory, but Ueno has many theories for the icicle ripples. But the icicle ripple reference, the first person to mention the existence of ripples on icicles is this guy, Toruhiko Terada, and he wrote a wonderful essay which has never been translated into English that I know of, called Stripe Patterns in Nature, way back in 1933, and he basically launched what we would call the pattern formation paradigm in Japan. And as far as I know, he's just not very well known outside Japan, although he was quite prolific at this field. So if you go to Japan, this type of physics, of pattern formation, or nonlinear physics that we would call it today, is called Terada physics, after this guy. So he's a kind of Japanese hero that we should all know more, but unfortunately most of his work has never been translated. I've only translated little snippets of this paper to learn what he had to say. But he observed both icicle ripples and ripples on stalactites and realized that they were similar to each other and discussed them way back in 1933. The first scientific paper published on icicle ripples is also from Japan. You'll notice a pattern here. Basically, everyone who's ever worked on icicle ripples is Japanese except me. Okay? This is most of the first paper. This is the word surara, which is the word icicle in Japanese, the only Japanese word I know, which is not a piece of sushi. And it basically says, I've noticed that icicles have ripples, and the ripples seem to always be about the same wavelength. And they say 8 millimeters here, which is pretty close to a centimeter. And this was published by Tozuka in 1938. Ironically, Tozuka does not cite Terada, so maybe he didn't know about it, I don't know. But I've made a little bit of a game of looking for people who have observed this before Terada, and I've never found anyone. So you can tell me if you know of somebody who did. So what do we know just from general observations about the ripples? First of all, they look sort of like the Michelin Man. They're not particularly sinusoidal. You see that they can be a little cuspy, okay? So there's one that's sort of cuspy. We discovered that they're not observed on distilled water icicles, and they are observed on impure water icicles. So they seem to have something to do with the water purity. They're always observed to have a wavelength very close to 1 centimeter. So I always say if you're out in the woods and you lose your meter stick, you can just break off the nearest icicle and the ripples will give you a handy reference for a centimeter. And if you look at my Canadian Tire meter stick here, you can count the bumps here, and it's very, very close to a centimeter. Unfortunately, all that theoretical work of Ogawa and Ueno, assumed that the ripples were some kind of pure water effect. So all the theories up to now have only used the thermodynamics of the growth of water and ignored completely the presence of the impurities in the water, which we now realize are crucial to the existence of the ripples. So Ueno has a theory, several theories, which blame the ripples on surface tension. And as I will show you, that just isn't so. Okay? First of all, you need concentration of salt to get the ripples, which is not in the theory. And secondly, when you manipulate the surface tension, it doesn't make any difference. And I'll show you that. Okay, so the cave ripples are also commonly observed. And they're also observed, although there's much less data on this, they're also observed to be approximately 1 centimeter in wavelength. And so these are sometimes seen on the sides of cave like it's called flowstone. But basically, as a stalactite grows, there's some conditions under which the stalactite will be discovered to be ripply. And those ripples are also found to be very close to 1 centimeter in wavelength, although there's just, I don't think anyone's ever studied it carefully except for these guys who wrote a theoretical paper just a few years ago on the ripples in stalactites. Here's, for example, if you look closely at this drapery that I showed you before, you see that it's all kind of corrugated into little ridges, and those are the 1 centimeter ripples. And they have a beautiful name, I forgot to say. In cave formations, they're known as crenulations. So maybe we should call them icicle crenulations, but nobody does. We call them ripples. Okay, so here's the crucial experiment. The only thing that affects the ripples significantly is the purity of the water. And we know that a purity around that of tap water makes nice ripples. So we set out to make an experiment using scientific tap water. We took distilled water and we added back to it pure sodium chloride in just the amount necessary to give a level of impurity which is similar to that of tap water. So this is a distilled water icicle. And all these icicles are growing at the same temperature and flow rate, and basically identical conditions except for the purity of the water. The first one is distilled, and you see that it's more transparent, and you'll also see that it's a bit bumpy, but the bumps are not organized into ripples, more or less. The middle one has about the salinity, about the same conductivity as Toronto tap water, which is kind of like New York tap water. It's, it tastes a little bit like pipes, And I can tell you exactly what's in the water because, of course, we took our water over to the chemistry department, had it analyzed completely so we could say what was in it. But this contains just 40 milligrams of sodium chloride per kilogram of H2O. That is a tiny impurity level. It's so small that you really have to have a chemist analyze it to measure it. Normal salinity meters can't measure that level. I remind you so this one is the same experiment run again with much, much more salt in it, 1.5 roughly grams of salt per kilogram. Now I remind you that seawater is something like 35 grams per kilogram, or what is it? It's like 20 times what this is. So none of these things approach the salinity of seawater, and in particular this one has an extremely low level of salinity compared to seawater, but it's still enough to produce the phenomenon that we're interested in, the ripples.
What's typical of rainwater?
I'll show you a slide of that. So that's an interesting question. How is it that natural icicles are rippled? And I'll show you why that is in a sec. Yeah?
Does it alter the freezing temperature?
Yes, but only by a very tiny amount, which I will tell you. That's got to be the effect, right? There's no chemistry going on, but it turns out to be a really tiny, tiny amount because this is such a tiny concentration. Okay, so what do we learn by studying? So what we do is we take 8 pictures per rotation. We can reconstruct the whole 3-dimensional shape of the icicle as a function of the time. We can extract those things. We can Fourier analyze them. We can do all kinds of things with the shape.
Am I right that it's really only changing amplitude, it's not changing the wavelength?
Correct. If you're really sharp, you'll see the waves are moving. But it's pretty hard to see in these pictures. Okay, so here is the distilled water icicle topography of one particular side spread out in time. And what I've done is I've detrended it by Fourier filtering out the long-term trends in the thing. And what you see is what survives the Fourier filter is not much topography, okay? This is sort of a yellow color. It's pretty close to 0. This is the tip of the icicle growing downward, and this is the sort of shape of the left side. I think it's the left side of the icicle spread out in time. So that's what distilled water looks like. It's not perfectly smooth, but it's not ripply either. This is the sort of tap water level ripply icicle. And you see these little bursts of ripples here and here. And what you see as you spread it out in time is that the ripples appear not quite at where the tip is, but a little while later they grow up to a few millimeters in amplitude, and they tend to appear in little patches. There are more ripples near the top of the icicle simply because this region has been growing longer than down here. This, the tip only reached here after 3 hours, so these guys down here haven't had a chance to grow much, but these ones have been growing for the whole lifetime of the icicle, basically, and yet they're little sort of wave packets, I like to call them. Wave packets of ripples are appearing on the ice. And here is the most salty icicle. This is about 1.3 grams per kilogram. And here the ripples grow almost immediately when the tip arrives at that location, and they grow to very high amplitude of maybe more than a millimeter in some cases. Okay, now remember we have full three-dimensional information, so we actually know how the ripples look all around the icicle in all directions. So and when the ripples are, when the icicle is grown from relatively salty water, the ripples can exhibit rather complex shapes. So this one, is rather blobby compared to the tap water level one. So if you look at the ripples from different directions, you see sometimes they exhibit kind of, collisions and starting and stopping and complicated dynamics. Okay, how do the ripples grow? How does their amplitude grow in time? Well, if I grow a distilled water icicle and I carefully look at the Fourier spectrum of the shape, there is some level of noise, and this is what a distilled water icicle looks like. That's the minimum sort of floor of my camera resolution. And if I look at a rather pure icicle, I can see the ripples growing and it's kind of leveling off here. If I add more salt, it grows up faster and it levels off at a higher amplitude. And so this shows that as I increase the amount of salt, not only does the growth rate increase, but also the final amplitude of the ripples gets larger. Now everybody knows that if you take water and you leave it around, it dissolves oxygen. It dissolves air. It doesn't dissolve much nitrogen, but it dissolves oxygen. So maybe that's what's causing the ripples. Now it's extremely difficult to do the experiment with water that's completely degassed because it takes 8 hours and the tank is not airtight. So we do the opposite thing. We take distilled water and we bubble air through it for 24 hours until it's totally saturated with air, and then we grow ripples from that. Okay, and what you find is pure distilled water with dissolved air doesn't produce anything different than distilled water that's not got dissolved air. So we don't think that dissolved air has anything to do with it. But all the icicles I'm going to show you, in fact, all the icicles that have ever existed probably have been saturated with dissolved air because they're made from thin film flows, and nobody's ever made an icicle which didn't have air around it, okay? At least as far as I know, okay? So the next thing you want to know is, well, what about surface tension? Wayno has a theory that says it's complicated to describe in detail, which I will in a few minutes, but basically the key parameter in his theory is the surface tension of the air-water interface on the outside of the icicle. Suppose we reduce that surface tension. So now you have a problem. You know if you put impurities in the water, that it will cause ripples to appear because we know impurities cause the ripples. What we need is a surface-active, surface tension reducing impurity which doesn't change the conductivity or the ice formation too much. It turns out there's a beautiful thing called Triton X, which is a non-ionic impurity. You can add it to water, it drops the surface tension by 50%, but it doesn't seem to change any of the other ice-growing properties of the thing. So it's dirty water, but surface-active dirty. If you drop the surface tension of distilled water with Triton X by 50% or so and grow icicles with it, it makes no effect whatsoever. Those icicles have no ripples. They're indistinguishable from distilled water icicles. So now you start to go a little crazy and you try some other things. You start mixing both Triton X and sodium chloride. By the way, we only use sodium chloride because we needed a simple ionic impurity similar to the stuff that was in the tap water, and we didn't want to start messing around with every possible impurity. I'll talk about that later. So I decided to buy some super pure sodium chloride from Sigma Aldrich. It costs like $300 a bottle. So I know exactly what's in that icicle. It's exactly sodium chloride and nothing else. Okay, so when you mix the Triton X and the sodium chloride together, the results are, we haven't done a lot of experiments like this, but the results are indistinguishable from just putting the salt in and not putting the Triton X in. As far as we can tell, the surface tension doesn't make any difference at all. Okay, so then, you go a little crazy and you do many, many trials with many different flow rates and temperatures and salinities, and you gather a great deal of data. And now I'm going to show you the kind of punchline of what you see when you look at all that data in various ways. Here, for example, is the rate at which the amplitude of the icicle grows as a function of the salinity over 4 orders of magnitude. Here, this is a 0 on a log scale. You should always be very suspicious of zeros on log scales, okay? But these are, as far as we know, 0 salinity icicles, and that's why the dotted line allows me to put 0 there. Okay, you bought it. You're mathematicians. You let me do it, okay? But this is the least amount of salt where we can see something. It's about 10 to the minus 3 weight percent, or 10 to the minus 5, and a few times 10 to the minus 5 in weight fraction. And they grow rather slowly. And as you increase the concentration, it's a little complicated. These are different flow rates and temperatures. But basically, it's linear in the logarithm of the concentration. So something is making these ripples grow, but it's very slow, logarithmic in the concentration. Now you're going to say, well, why the heck is that? And the answer is we haven't any idea. Okay, when I talk about the theory, you're going to hear that we just don't know why any of these things happen. Sorry, that's how it is. Okay, so they grow roughly like log C. Around 0.1 weight percent, the data gets very noisy, and that's because up at these high salinities, the icicle has that blobby shape that I was showing you, and the ripples are a little harder to get their amplitudes and stuff. But lower than that, the ripples are fairly straightforward to measure. I mentioned that the ripples are always seen to have a wavelength of 1 centimeter, and here is the data for that. It's completely independent of the flow rate. It's independent of the amplitude of the ripples. In other words, they don't show any amplitude nonlinear behavior. It's independent of the temperature, and over 4 orders of magnitude of salinity, basically we see 1 centimeter as the wavelength of the ripples for this impurity. There is some small indication in recent data that the ripple wavelength might depend very slightly on the species of the impurity, but I don't have enough data to say that yet. Yeah?
Aside from the surfactant and the sodium chloride, what other impurities have you tried?
We've tried a sort of a garden variety sugar. We've tried copper sulfate. We've tried various masses of polyethylene glycol, which is a soluble polymer you can buy in different molecular weights. And the answer is nothing dramatic jumps out at us from those things.
Are you going to tell us which ones grow ripples?
They all grow ripples.
So it's not specifically that it's an ionic compound?
No.
Okay.
No, dextrose, for example, grows ripples. Yeah. Yeah. Yeah.
I just wondered, in your icicle, all 3 modes are contributed to the growth, or you see primarily some modes? You mentioned there's a tip grow, there's the infill grow, and there's also the third one, side grow.
This is all side grow. Okay. The tip is, just a totally different process, not related to the ripples.
This is all lateral growth.
Yeah, it's simply the radius of the upper part of the icicle getting thicker at a pretty constant rate. I'm not showing you the underlying rate, but it grows pretty constantly and it grows faster if you're colder, it goes faster if you put more or less water through. But the ripples on top of that grow, the way I've been showing you. Yeah.
And the little bars are standard deviation?
Yeah.
Right? And there are little bars on those dots?
Yeah, there's some. Yeah.
Wow. Okay.
Okay, this is all different. The colors are all different flow rates and stuff. Okay, now here's the funniest one. So we don't know why it's a centimeter, okay? So that's one of the underlying mysteries. That was known before. The Japanese observers have written papers in which they looked at natural icicles many different ways, and they all see 1 centimeter ripples plus or minus the error bar on natural icicles. So there's no reason to think these ripples are any different than natural icicles. We just have much better data than you can get from natural icicles. Here is the traveling speed. It turns out there's no symmetry for these ripples. Down the icicle is different than up the icicle. The water is flowing down, it's not flowing up. So generically, there's no reason for the ripples to be stationary, and they're not stationary. For low values of salinity, they travel upward very slowly. So over the whole 8 hours or 4 hours of growth, they might move a few wavelengths upward. And here is a space-time picture. And what we do is we fit the peaks of a few selected ripples here, and you see them sloping upward. So they move a few tenths of a centimeter per hour. And as you increase the salinity, there's this funny 0.1 weight percent. and the ripples get much more complex in their motion at high salinity, but on average, we find that they move down. Now, this is kind of funny because Ogawa's theory predicted the ripples should move down, and Ueno's theory predicted the ripples should move up. So we have two theories, two possible signs, two theorists, right? Everything matches beautifully, and the data actually is completely agnostic. They move in both directions depending on the salinity. We don't know why this is at all. It's one of the key, and why this sort of magic crossover salinity happens. There is very tiny shreds of evidence for the motion of ripples on stalactites. I visited the Okinawa Institute of Technology, Okinawa Institute of Science and Technology, and I happened to meet Mirona Chirienko, who collects stalagmites and stalactites and uses them for geochronology. So this is actually a little sample taken from a section stalagmite, actually, stalagmite being the one on the floor and not on the ceiling. And as soon as she showed it to me, I said, holy cow, I can see the ripples moving. You see them? And if I put some lines on there, you'll believe me that these ripples are actually traveling upward as a function of growth. So the ripples, it's the same sort of thing as happens on the icicle, only traveling upward. Now, the difference, of course, is that this is 50,000 or 100,000 years of growth, whereas the icicle does it all in a few hours. I don't know that anyone has ever systematically studied the motion of ripples on section stalactites, but you certainly could do it. And the reason is that people often section stalactites for doing these climate temperature proxy studies. It's one of the main things they use for deducing ancient CO2 at climate. So I don't want to leave you with the impression that all it ever does is grow and saturate. It turns out that more complex things can happen. If I use a rather low temperature and a rather low flow rate, then it's possible for the icicle to stop growing at the tip. And the reason for that is, as the water is flowing down the icicle, it's freezing out. And if it's rather slow flow rate and low temperature, it can freeze out all the water before it reaches the tip. And so that's what we call cessation. So this icicle just stopped here, and that was going to stop down here somewhere. If you watch the ripples evolve on icicles which are in this funny limit of cessation, they will often show more complicated time dependence. So this one here, if you look at the ripples up there, they grow really big for a while, then they die out again. It turns out that the conditions of constant flow rate and temperature are not constant fluid mechanical conditions because the film is getting thinner because the icicle is getting larger, and so it's a kind of more complicated experiment, and we don't really know why it comes down again, but it does. Now, someone asked about natural icicles. A couple of winters ago, I snuck around in the back lanes near my house and swiped icicles off my neighbors' roofs. And I put them in Dalgene bottles, and I took them to the chemistry lab and had them analyzed. And I can tell you that there's a huge diversity in the salinity and impurities in natural icicles. But we can see ripples on icicles with as small as 7 microsiemens per centimeter. That's a conductivity measure. And typical icicles that we're seeing on people's roofs can often have salinities which are 10 times that. So this icicle here, which is clearly ripply, has about 3 times the threshold level of salinity, of impurity levels in it. And so the fact that it appears to be ripply is not inconsistent with the laboratory experiments. Now, nobody has done a systematic study of the ripples on natural icicles versus their salinity. If you care to do that, I'd be happy to help you. But we haven't done it systematically, but we believe that the natural icicles you see with ripples on them have sufficient impurities in the water that there's no inconsistency with the laboratory experiment. Yeah?
Have you specifically grown sea icicles?
No.
Basically seawater above.
No. Other people have, and they're much more complicated in their shape than...
Okay, because by the way, I just in my bank of polar photos found essentially seawater rhyming with all sorts of ripples.
Yeah.
I think you'd be really interested.
Yeah. So next time you're in Antarctica, you know what to do, right? Collect them.
And bring them back.
Bring them back. Or just take a picture with a ruler next to it. That would be pretty good, too. People have studied marine icing for engineering applications, and they do observe that there are papers in which they mention that they're bumpier and ripplier. But no one had ever systematically made the connection between salt and... But seawater is like 20 times the salinity of these things. Okay, so we think that natural icicles are ripply for the same reason. Okay, that concludes the experimental and curious observational portion of the talk. The rest of what I'm going to tell you is theory, and I'm not really a theorist. And all the theory I'm going to tell you is either half-baked or failed or has problems. And we're actively working on the theory, but I think it eventually I hope I can show that it makes some contact with the things that you're interested in. That's why I'm here, I guess. Yeah?
You mentioned that you control the humidity, and I wondered, have you experimented with varying the humidity? And
Well, okay, I used the wrong word there. We measure the humidity.
yeah,
And in future experiments, which we're still running experiments, we're going to control it.
yeah,
You have a box, it's at low temperature, and you're pouring water into it. The humidity rises to 100%, basically. What we're going to do next is ventilate the box with dry air to drop the humidity. And it turns out that a significant fraction of the heat transfer is due to evaporation. I'm going to talk about that in a second. So the humidity matters mainly for the evaporative heat transfer. And that does happen.
but, I mean, that would concentrate impurities.
It doesn't it's a significant heat transfer, but it's not a significant mass transfer. So we don't evaporate a significant fraction of the water. It is a significant heat transfer, though, and it turns out that low humidity will grow icicles way better than high humidity will. Okay, so the first thing you need to know is that this is an experiment which is driven experimentally by huge temperature differences like -12. The icicle is growing around somewhere close to the freezing temperature. The wall of the box might be -10, -20. Most of the time we use something between -10 and -20. So you might think this is a strongly driven large temperature gradient, but that's not true. The reason is that there's a very, very thin film of water running over the surface of the ice, and it's surrounded by all this air, which is turbulently moving and transferring heat. And this conductivity of the water is so much higher than that of the air that almost all the temperature differences across the air, and only a tiny temperature drop is across the water. We know from the rate at which the ice grows, we know how much heat has to be removed, and we can turn that from the latent heat, we can turn that into a temperature difference, approximate temperature difference, and it turns out to be millikelvin. This film is super cooled by just a few tens or maybe 100 millikelvin from zero. Whereas the air has this huge temperature difference across it. All the water in the experiment is super cooled, but only by a tiny, tiny fraction of a degree. Furthermore, you know that you have something called the Stefan condition, which tells you that the latent heat times the velocity at which the ice is growing has to be accounted for by the heat transfer. So this is the thermal conductivity and the temperature gradient at the ice-water interface. But on the outside, where the air-water interface occurs, it turns out, and this is actually Jerome Neufeld, who's sitting at the back, discovered this. He actually did the experiment where you melt a piece of ice rather than watch it grow, but it's similar from the reverse direction heat transfer. It turns out that all forms of heat transfer are active in the air. There's advection diffusion through turbulent boundary layer because we're stirring the air. It turns out if you calculate the heat flux due to the evaporation, because of what we were saying a minute ago about the humidity, that turns out to be a significant thing. And even radiation turns out to be a significant form of heat transfer. So this is like the heat transfer problem from hell on the outside of the icicle. Okay? So these turn out to all be about the same size. Okay, so that's a little daunting. Okay? But essentially every phenomena that can remove heat from the surface of the water is acting in the air. Now what about the presence of salt? You know that if you have a tiny concentration of salt, that there's a solidus line and a liquidus line, which are basically straight. This is pure water, and this drops as a function of the added salt linearly with slope m. And so the water that's up against the surface of the growing icicle, it might have some trapped salinity in it, but it basically excludes the salt as it grows and piles up salinity in front of the growing surface of the ice. And the temperature at which that occurs is reduced by something proportional to the concentration of salt at the surface by this liquidus slope. It turns out, so Tm is the equilibrium melting temperature. So we suggest that the boundary condition on the temperature at the surface of the growing ice has to be the equilibrium temperature minus something proportional to the concentration of salt. It turns out that if you calculate how big is that effect for the tiny salinities that we're talking about, it turns out that the depression of the freezing temperature due to that small concentration of salt compared to the temperature difference across the water film in the first place is order 1. So that means that the salinity effect is itself only 50, 100 millikelvin. It's really tiny because these are very tiny amounts of salt, okay? So if you want to know why is the icicle so sensitive to tiny impurities, the answer is the whole experiment is driven by tiny little temperature differences. If you drop the freezing temperature by 50 millikelvin, that's a big effect, actually. Unfortunately, there's another effect which is known to be significant at these tiny temperature differences, and that is a kinetic effect. If this is just a phenomenological kinetic coefficient, but the ice water temperature will actually also be dropped if you grow ice at finite speed. And these phenomena are kinetic in nature, and they're non-equilibrium, and they're known to be something in the millikelvin at this speed as well. So there's probably kinetic effects in the phenomenon as well. Okay, so I'll come back in a minute to what Ueno did in his theory, and I'll describe a theory that we put together to try and understand the linear instability of the water, of the ice, growing ice, using only the properties of the heat and mass and heat and salt transfer in the flowing water film. So what we do is we basically assume that we have a parabolic shear flow in the base state. So this thing is just stable and running down this flat, infinitely flat icicle, and we're going to perturb this surface and calculate how that perturbation either grows or decays by solving the fluid problem first and then solving the advection diffusion problem for heat and salt through the flowing water layer. And that leads to a fourth order or Sommerfeld sort of shear problem where you have the rigid boundary condition on the inside, you have deformable surfaces on both sides, and you have a surface tension on the outside of the icicle. It turns out you can solve this. It depends on the Reynolds number and the Weber number, but not independently. It actually depends on the cube of the wave number and this funny combination of Reynolds and Weber. So there's only one dimensionless parameter in there. So we can solve for, take my icicle, put an infinitesimal perturbation on its surface of some wave number k. What does that do to the water flow? And it deforms the free surface. It leads to a secondary flow which transports heat and salt toward and away from the surface. So we put that into two advection diffusion equations, one for the temperature and one for the concentration. And the Peclet number for the temperature turns out to be not very big, about 5. And the Peclet number for salt, because it diffuses so much more slowly, is about 400. We actually keep this even though we could probably go to the Peclet number infinity limit cleanly. We don't. If you know your Stefan problems, there's another dimensionless number, which is the Stefan number, and it turns out to be large. That means that this is the sort of easy limit of growth. You don't expect terrible things to happen at low Stefan numbers, but at high Stefan numbers, you're kind of safe. So now we have to try to close the problem. We put the perturbation on the ice-water interface. We have the Stefan condition and other conditions on that interface, and we try to calculate whether the advection and diffusion causes those ripples to grow or decay, linear stability. And that leads to the infamous problem of boundary conditions. Like, this is the joke I always tell when I teach fluid mechanics. There are only 3 problems in fluid mechanics, and they are boundary conditions, boundary conditions, boundary conditions. Hilarious, right? So here's G.I. Taylor. By the way, if anyone would like to accompany me to the resting place of G.I., which is, I know where it is, so I will show it to you this afternoon on our way to dinner, if you're interested. I usually actually attribute this joke to von Karman, who's a much funnier guy, certainly funnier than Prandtl, okay? Anyway, so here's the sketch of the theory. There are 4 fluid dynamical boundary conditions. Those are uncontroversial. There are 2 conditions on the salt concentration. Basically, you don't let the salt leave the free surface, and you make the salt gradient of the salt appear as the ice grows. It excludes the salt. There's the Stefan condition, which links the growth rate to the temperature gradient. And it turns out that physically at the free surface, the water-air surface, neither the gradient of the temperature nor the temperature itself is constrained, but actually a linear combination of the two is constrained. So there's what's called a Robin condition on the free surface for delta T and delta T. So all these are relatively straightforward, except for there's 9 boundary conditions. There's only 2 that are sort of where the physics is tricky. Okay, the first one I just mentioned is you have to make a model for the turbulent heat transfer and all that stuff in the air, and that gives you this value, this dimensionless number lambda, and you can figure this one out. And the other one is the temperature at the ice water surface, including kinetic effects and concentration. Okay, so you put that all in, you crank, and this took me months, okay? And you end up with this. What?
Question, Stephen.
Yeah.
The z equals 0 in the previous slide, is that in a moving frame?
No.
Okay.
The moving frame comes in later, but I just, okay, it's not moving.
Okay.
We can talk about that. All right, so this is what the perturbed stream function looks like. These are the ice, this is the ice surface, and this is an exaggerated topography of the assumed ripple on that surface. And the little arrows show the direction in which the fluid is flowing toward and away from the free surface as a result of the perturbation of those ripples. And this is just from linear or Sommerfeld. And then when you put that into the advection diffusion equation for heat, you discover that at Peckley number 5 and with the boundary conditions that you have on the temperature, it hardly makes any difference to the temperature field. It doesn't advect it very much. Basically, the peaks of the ripples are growing faster. They're evolving heat faster. That warms up the surface out here, and the heat transfer carries the heat away. So it turns out that the water is basically at the same temperature on both sides. The perturbation of the temperature is the same. One interesting thing is that you see that the ripple on the free surface is actually a little bit upstream of the ripple on the solid surface, and that's the surface tension effect. So maybe that explains why the icicle ripples tend to move upward. The solidity is more interesting. It cannot pass through the outer surface. It's generated on the surface wherever the ripple is growing. There's more salt. Wherever it's not growing or growing less fast, it's producing less salt. So we can solve all those equations. Now we try to close the loop and we calculate the growth rate of the ripple from linear stability. And the equations blow up, okay? It completely fails to account for the wavelength selection, basically because the eigenvalue just grows. This is the dimensionless wave number. The eigenvalue just grows to infinity at large k. So it's a kind of ultraviolet catastrophe. Somewhere we've left out some physics, and the physics would tell us that small wavelength ripples or somehow have a smaller growth rate than larger wavelength ripples do. But there's no such physics in this model, and we get that infinitely small wavelength ripples grow infinitely fast. Yeah?
And your dimensionless K is, what's the length scale you scale that on?
The kinetic term. I guess I don't have a clean answer for that. All I know is that I tried all sorts of values of K and I didn't get the thing to convert.
So the thickness of the film, does that?
Yes. The thickness of the film is the length scale that we use. And the velocity, I used plausible values for the kinetic coefficient, but I didn't work. So this is very generic. You can try everything, and basically there's physics missing. So here's Wayno's theory. He gets a growth rate that goes from 0 and cuts off at some small value of k, and the peak is right at a centimeter, inverse of a centimeter. So he actually gets a prediction for the wavelength. But remember, his theory has no salt in it. How does he do that? Well, the answer is that he doesn't use the same temperature boundary conditions. He assumes instead the two boundary conditions on the advection diffusion equation for the temperature are both applied at the air-water interface. So instead of constraining this linear combination of T and grad T, he has T and grad T constrained separately. That's two conditions. There's no temperature boundary condition on the ice-water interface in Wayno's theory. Okay? If you do that, then the surface tension at the free surface does punish small wavelength ripples because surface tension punishes small wavelengths. And the theory has a cutoff, and what do you know? You get the right wavelength approximately. But there's no salt in the theory, okay? And we showed that when you change the surface tension, it doesn't make any difference. And the real killer is, now we want to put salt in the theory. The only place it can matter is at the water-ice interface where the temperature is dropped by the salinity. And there's no boundary condition to change in this theory, so you can't do it, right? You cannot have no boundary condition on the temperature and include the salt. So Wayno's theory gives you the right answer, but the physics of this cutoff just can't be right. Now, I should mention that this Ridolfi Campo-Reale theory for stalactites, the situation in stalactite growth is considerably more complex. Basically, it's the same kind of theory, except there's chemistry going on. There's three species, and there's rate equations between these three species in the flowing water film. It turns out that there's an analog of the Stefan condition at this surface, which is that it's the flux of the growth of the calcium carbonate is proportional to the gradient of the calcium ion concentration. And so that's like the analog of the Stefan condition. And then there's a separate boundary condition on the concentration at the air-water interface here. And what they do is they put in that there's a constant value of the CO2 concentration equal to that of the air outside the stalactite, and they put that in at the outside surface. That is a physically different boundary condition than the one we have on the temperature, and it's similar to what Wayno's temperature boundary condition is. It's a constant there. And for that reason, their theory closes. They get a growth rate that has a short wavelength cutoff, and what do you know? The wavelength is 1 centimeter. Okay, but we don't have the luxury of doing that because we don't have the right physics in the boundary condition. We don't have the same physics in the boundary condition. Okay, well, so what's really going on? Now I'm going to tell you what you probably already have guessed, which is that mushy layers have something to do with this, okay? What's really going on is at the small scale, this is water growing into a supercooled melt, as you would call it, supercooled water. That's a terrifically unstable process at the small scale. It's unstable to dendritic growth. Okay, and the dendrites have a length scale which is very small compared to the ripples. This is a 1 millimeter bar here. There's something called the Mullen-Sakirka length scale, which tells you roughly the radius of curvature of these things, or the spacing between the little legs on the dendrite, and that's around 100 microns in this experiment. So down at the small scale, there's surface tension between the water and the ice, and it's punishing curvatures of the surface, but only really tiny ones. And the ice is not smooth like we've been assuming. It's actually a little forest of dendrites competing with one another. And it's even worse because if you talk to the people who work in the business of engineering power line ice buildup or airplane ice buildup, they're typically talking about the growth of what they call spongy ice. This is ice grown from pure supercooled water on, say, a power line during a rainstorm. And they find experimentally that up to 25% of that water does not freeze. It's actually trapped between the dendrites as they grow. And because, again, there's no temperature gradients left, you actually get water and ice, pure water and pure ice at equilibrium with each other back behind the front. So not all of the ice solidifies, not all the water solidifies. A whole lot of it doesn't solidify. It is trapped in the matrix. Okay? And as long as you continue to supply water, the latent heat holds the whole icicle, in this case, up at 0 degrees, and all that water and ice is at equilibrium. So it's spongy, okay? Now we add a little tiny pinch of salt, and we have a mushy layer, okay? Because that's the kind of physics of slightly impure growth is what you guys would call mushy layer. But it's in the limit of small concentration of mush. Okay, so we either have a mushy layer with very, very little concentration of impurity in it, or we have some kind of kinetic mushy layer, which is what the engineers call spongy ice. Okay? And it's believed by the engineers that up to 25% of the water is trapped inside the icicle without freezing. Okay? And that's a purely kinetic effect. Okay, so here's a picture that you probably would like to see, which is what does the inside crystal structure look like in the icicle? It turns out that icicles are polycrystalline composite materials with millimeter-sized crystals. The orientation, people talk about the different orientations of crystal, and there's a whole crystal growth problem inside the icicle. If you look at the thesis of the Japanese student who worked on this, who did look at the sections of Ripley icicles, here's a ripple. So you see that the polycrystals are smaller than the ripples by quite a bit. So what we really have is a complex material, not just a homogeneous thing that we've treated so far. And I suspect that because we have tiny amounts of salt mattering, that this has actually got a little bit of melt in it, at least a little bit. And the engineers would say that it may have as much as 25% melt in it, even if it's completely pure. So this is some kind of complicated material, not just a simple homogeneous material. So, okay, so now I come to the punchline, I guess, for you guys, which is how do we take our theory, which diverges at the small wavelengths, and how do we put in the physics necessary to cut off that divergence by using the fact that the ice is some kind of spongy thing. Here's the theory that I've described so far. It has some boundary condition where the latent heat is released completely and the salt is excluded completely at this sharp inner boundary, and the outer surface is deformable and all of that. If I replace the ice with some kind of spongy or mushy thing, then all of a sudden I have a mushy layer with a flow on the outside of it, The inside of the mushy layer is described by a temperature which isn't uniform inside. It has a concentration which is smoothed out inside. The usual assumption of a mushy layer has an local equilibrium between the concentration and the temperature inside the mush. It's also porous, so that if there's pressure differences on this surface, it can drive Darcy law flow inside. That can advect and diffuse both heat and salt inside of the icicle. And that somehow, I hope to claim, that somehow smooths out the surface at short wavelengths and cuts off the short wavelength divergence. Okay, so what I call the outer flows we've already solved for, but we haven't solved yet for the inner flow, the Darcy law flow inside of the icicle, if there is one. And there's a paper where a problem similar to this was solved by Feltham and Worcester and corrected later by Jerome, I should have said. I should have put you down here. Jerome and Neufeld and Worcester wrote a second paper about this phenomenon. And the basic physics is quite simple. You have some kind of outer flow here, and if you have an undulation on your surface of your mush, then that gives rise to pressures on that surface which can drive Darcy law flow inside, and that carries heat and salt from the minima of the undulations up to the peaks. Okay, and that's actually in the right direction, because that would deliver salt to the growing peaks, and that makes them colder and grow less fast. Okay, so basically, what I hope the spongy theory will do is that it will smear out the release of latent heat and salt over some kind of length scale of the sponginess or the mushiness, and that will provide the physics for the short wavelength cutoff. This is work in progress. We don't know that this works yet. We're trying to take this paper and generalize it to a thin film flow on the outside and put in all the physics, which is actually the temperature gradient is in the opposite direction in this experiment than it is in this paper, and there's other details. Okay, so that's the connection. That's why I'm here, I guess, other than to provide pre-dinner entertainment. So I'm finished. There are lots of questions. What stabilizes a pure water icicle? If I take away all the salt, then everything's kinetic, right? And the engineers tell me that there's a whole kinetic spongy layer, spongy ice in there. There's not a mushy layer. It can't have local equilibrium because there's no salt, okay? So how do you do that? And we were having a big conversation yesterday trying to figure out how to get spongy ice. We want to try different impurities. We want to try things like antifreeze proteins and things that have dramatically different liquidus slopes. If we put dye in, use dye as an impurity, then we're doing the kind of beet juice experiment that was done in Antarctica, where we can see where hopefully we can see where the flow is inside of the icicle. And I'd like eventually to also grow stalactites if I can find a really, really patient graduate student. So you asked about other impurities. So here's the world's first dextrose icicle. If you break it off and eat it, it's kind of sweet the sugar icicle.
Isn't there a science lab kit that they give to kids that make stalactites?
It's not the same chemistry.
It's
evaporation. Yeah.
Okay.
When I say make, I mean make an accurate laboratory analog and not something that just looks like one.
Okay.
Yeah. It's harder. It can be done, but it's a little harder. Let me just finish up by showing you something which I hope will amuse you. At the end of this experiment, Anthony Chen had taken 230,000 images of growing icicles. That's the data I showed you. I thought it was a waste not to release these into the wild. So what I did was I created something called the Icicle Atlas. If you Google Icicle Atlas, you'll find this page. Every icicle we grew has a little home page. Every image, every movie, all the data, all the time series are all open access data online. You can do whatever you want with it. If you want to analyze it again, please do. Here's what I call the Icicle Rogues Gallery. This is a small sample. You can go and you can click on any of these and find out everything you ever wanted to know about that icicle. And many of these icicles with ripples were scanned in 3 dimensions, which means that we can actually reconstruct them with a 3D printer. So here is a scaled down 3D printed icicle with ripples. This is actually about that long, but it's been scaled down by a factor of about 3. And so the ripples are like 1/3 of a centimeter instead of a centimeter. And you can go to this site and download hundreds of these 3D printable icicles at your leisure, okay? And you can handle this one.
Did airport security ask you about that?
It's plastic. X-ray, just go right through it. I haven't tried to make any gold ones, so here's a picture of it. So this is an icicle which melted something like 4 or 5 years ago, but here it is reliving in plastic. And here's another example of things that I've been doing. I've been compositing movies. I've actually had art shows in which I use composited pictures of icicles for many different conditions. It's been covered in the New York Times, and so we're having a lot of fun with the data. Thanks very much for your attention, and I'll take questions. Yeah.
Can you image what happens in the air around on the outside of that thin film?
No. We originally wanted to, but it never happened. There's every reason to think that there's a turbulent, viscous, and thermal boundary layer there, which is pretty thin. One thing I didn't mention, which is another strange, unexplained effect, we originally were going to do the experiment in still air. And the reason we wanted to do still air, as you know, is that we wanted to look at the gravity current and whatever. And the original shape theory for icicles was predicated on the idea that the heat transfer through a sort of a non-turbulent boundary layer around the icicle was somehow determining the shape. But what we found when we did the experiment with still air was that the icicles had a habit of growing multiple tips. So in fact, that one is a multiple tipped icicle. Okay? So basically, we couldn't analyze the data because every time we did the experiment, we tended to get multiple tips. Then if you stir the air in the box pretty violently, two good things happen. One, the icicle grows faster because the heat transfers faster. And secondly, no more multiple tips, or almost none. Why, you're going to say, well, we don't know. Something about the thinness of the boundary layer when you're in the stirred case suppresses these little prongs that stick out occasionally and cause secondary tips, but we don't know why. Yeah?
Have you removed your impurities when you do the linear stability analysis? Or you just do the heat transfer?
Yeah, it just blows up.
So the curve goes up higher, quicker than...
Yeah. The rate at which it grows is a complicated function of parameters.
As a function of wavelength, you're telling me.
Yeah. In fact, Wayno knows this. He did solve it with the boundary condition without the salt, with the TM on the inside edge. And he rejected that boundary condition because the linear stability blew up.
So both blow up.
That's correct. So our blow up is not any different than Wayno's blow up. It's just that because we're going to include the salt, we're forced to put the boundary condition on the ice water surface. And physically, it has to be there. Yeah?
Is it possible to grow saltsicles on the other side of the eutectic?
That is an interesting question. Yes, those would be like marine icicles. I'm not sure where they are in relation to the eutectic concentration, but yeah, in principle, sure.
Well, the solid would be salt. Is that the same as
Oh, yeah. No, I don't. I guess. I didn't think of that. That's interesting. I don't know. People have done marine icicles, but not much farther in salinity than that. Because of, who cares about super salty icicles? Come on.
They're not icicles, they're salts.
I care. Am I a nobody? Yeah, another question I'm often asked is, why don't you grow an icicle out of something that's not water? And the answer to that is, what exactly? It turns out that most organic things like alcohol, they evaporate too much and you fill the room with alcohol, which is going to explode. They're not safe, okay? You can't do it in the lab. Other things like wax are not dispersed enough in their molecules to have a sharp melting freezing transition, so they're kind of mushy all the time. The only thing we've come up with is liquid gallium, which is a nice metal which melts at 38 degrees or something like that. But I can't afford the gallium to try the experiment, so we haven't done that one. But if you think of a material, it has to be a pure material, has to have a sharp melting freezing temperature, which isn't too far from room temperature, and it has to not have a vapor pressure that's going to kill you, okay? So there aren't too many materials other than water. So we haven't done it.
Any other questions for Stephen?
Yeah.
Yeah, is there any chance that the fact that the water has a volume change when the phase changes, the volume change that is different than any other?
Yeah, I left that out. Of the model doesn't have that in there, but standard mushy layer theory can have that put in. And that gives you a divergence of the Darcy law of flow. Wherever the freezing occurs, it excludes some of the water. So we could put that in. But I don't have any sense whether that's important physics or not. It might be.
All right, let's thank Stephen again.
Thank you.